Hello and welcome back. In this video, we'll discuss higher order partial derivatives. We'll work through an example where we find some higher order partial derivatives. And finally, we'll talk about Claro's theorem, which gives us a condition which guarantees equality among mixed partial derivatives. So you'll understand what I'm saying in a little bit by that. So I want to start by, before I talk about all these new symbols, these higher order partial derivatives, I want to jump up to an example we saw in a video where we computed fx and fy of this function of two variables. Right, we found fx was 2xy and fy was x squared. Now in general, when we compute these partial derivatives, the output is a function of two variables, the same number of variables we started with. So when you do a partial derivative, you end up again with a function of two variables. Just because I take an x partial derivative doesn't mean I'm going to eliminate all the x's or all the y's. I could still have x's and y's in there. Just like we saw here with fx, we have 2xy. So in general, fx and fy are functions of the two variables that we started with, which means we can take partial derivatives again. So if we want to understand, say, how the x partial derivative changes, the rate of change of the x partial derivative as we move in the x direction, that would be taking the x partial derivative of the x partial derivative. So that would be fxx is one way to say this. We could investigate how the x partial derivative changes, so the rate of change of that as we move in the y direction, that would be fxy. Right, fxy, and then all the other ones, right? We would have fyy and fyx. So we actually get four partial second order partial derivatives. So we would call these second order because we take two derivatives to get to them. So there are four second order partial derivatives. Of course, we can keep going. There would be 8 third order partial derivatives, because each one of these I could then differentiate with respect to either x or y, right? I would have fxxx, fxxy, and same for each of these. Now those are gonna, so I said eight for third order partial derivatives, but we'll see a theorem in a second that's gonna guarantee some equality between those. But in general, there would be 8 third order, or 4 second order, and just the 2 first order. And that's for a function of 2 variables. All right, so let's actually compute these. Not a whole lot new here. It's just we'd first need to find, if I want, say, all of the second partial derivatives of f, the second order partial derivatives, I need to first find the first order, so just fx and fy, and then each of those I'm going to differentiate with respect to x or y. So let's go ahead and find fx first. Let's find my first partials. So differentiate with respect to x. Remember, we're going to treat y as a constant. So I have 3y times x to the fourth, so that's going to be 12x cubed y minus y is a constant, so I should just get 2y here, plus differentiating with respect to x, 5y cubed. So there's fx. I'll put fy over here. I should get 3x to the fourth minus 2x plus, what, 15xy squared. Right there, we're treating x as a constant. So there's my first orders. Now I want to find all my second orders, and that means just take these functions that we got, my first orders, and differentiate again with respect to x and y. So let's compute fxy. So this is the partial derivative with respect to y of fx. So now I'm differentiating this one with respect to y. So I'll have 12x cubed, right? I'm treating x here as a constant, minus 2, that y will go away, plus 15y squared. So that's fxy, the y partial of the x partial. Let's do fxx. So that's the x partial of the x partial. So here I'll treat y as a constant and differentiate with respect to x. So I'll get 36x squared y. 2y has no x's in it, so this is a constant in the eyes of x, so that goes to 0. And same thing here, 5y cubed, that goes to 0. It has no x's in it, so it's just 36x squared y. Cool. So there are these two partials. Let's now differentiate y with respect to x and y. So how about we do fyx first? So I'll do the x partial of f sub y. All right, so that's going to be 12x cubed minus 2 plus 15y squared. Cool. And finally, fyy, the y partial of the y partial. So this is a constant with respect to y. This is a constant with respect to y. So both of those go to 0. And what we have here, we'll have 30xy. So this is 30xy. And there we go. There's all 4 of the second partial derivatives of f. Now I want to point something out here, that fxy is the same as fyx. So that's a curiosity. I mean, fxx and fyy, these are distinct from each other and the other ones, the mixed partials. But these two are equal to each other. So that's kind of interesting. And at this point, we could ask a good question. That is, is this always going to be the case? Are the mixed partial derivative, fxy and fyx, are these always going to be equal to each other no matter what function we pick? Well, the short answer is no, not generally. There are functions that break it. So if the answer is no, then under what conditions are we guaranteed for those mixed partials to be equal to each other? Now that is the subject of Claro's theorem. So I'll go ahead and uncover Claro's theorem here. So Claro's theorem tells us when that is going to work, when the mixed partials are equal to each other. And the idea is this. So we have a function. If we can find our function defined on some open set in R2, if fxy and fyx, the mixed partials, are continuous throughout D, so if they're continuous, then they will be equal at all points of D. So if we can somehow figure out, say before differentiating, that these are going to be continuous, so say by looking at the functions and analyzing the functions, then we can be guaranteed that these are going to be equal to each other at all points in the domain. Now, Claro's theorem, given sufficient continuity, so Claro's theorem can be extended to even higher order partial derivatives, right? So, for example, mixed partials like fxyx and xxy and yxx, right? So there's one y partial and two x partials in each of these, right? Two x's and one y. Claro's theorem says that if each of these are continuous, then they are equal to each other. And that's the same if I have the same number of x's and the same number of y's. Those partials, those mixed partials, will be equal to each other so long as each is continuous on the domain. So that's really what we need. We need continuity of those mixed partials, and then we're guaranteed they're equal. And that's going to come in handy. All right, that's it for this video. I'll see you next time.